I'm Andy Evans. I work with Melanoma Patient Network Europe. You can probably tell from my voice that I'm not originally from Europe. I'm originally from the US, but I moved to Amsterdam a few years ago. So I'm honorarily Dutch, although Dick will give me trouble because I haven't learned enough Dutch yet. So just a really quick intro to me and why I'm here. I'm in an interesting position. I'm kind of between two worlds. I'm a patient. I was diagnosed with ocular melanoma in 2013 in the States. But at the time that I was diagnosed, I was also working in the field of bioinformatics. I was trained as a molecular biologist, and I was working on cancer diagnostics at the time. So I have maybe too much knowledge for a patient about what was going on. In fact, I had the very unusual and uncomfortable situation of having some software that the team that I was working with had built being used to process my own cancer diagnostic. So I don't recommend testing software that way. It's not really how you want to do it. So really quick, if everyone raise your hands, just everyone put up one hand. If you are a professional or an academe or a researcher who's working in cancer or in molecular biology or a related field, go ahead and put your hand down. All right? If you are someone who's just really into cell biology and you've been, it's just even before you were diagnosed as a patient or whatever, you were studying it and you know a lot about cell biology, put your hand down. All right, so the people who are left here, you all are probably a good target audience for what we're going to talk about next. So if you keep your hand up, if before you were diagnosed or became a caregiver for someone who was diagnosed or became involved in this, you really had no idea what cancer biology was, and you probably didn't think you were going to have to care about it ever. It's still a lot of us, right? All right. So this is the situation. You can put your hands down. Thanks. So this is the situation that patients we often find ourselves in. Even someone like me, I was, pretty up on the field. This really caught me off guard, and there was a lot that I didn't know about this disease and the terminology and the mechanics of cancer. And it's not something that I really thought I'd ever have to apply to myself. I mean, a third of us are going to get cancer at some point or another, so maybe that was unrealistic to expect, but it's not something that really occurs to you until it happens, right? So, we were all kind of cruising along with our lives happily, not thinking about cancer, and then we or someone we love got sick, right? So, as we just heard, Vikas, he just gave a really excellent overview of what cancer is about. I'm going to bring it to you from a slightly different angle. Because I'm a bioinformatician, I look at cancer maybe slightly differently from the way some of the other researchers who've been speaking to you and the clinicians think about it. I think about it as a disease of corrupted information. As Vikas was pointing out, with DNA being encoded with letters on the molecule, it's a disease of corrupted information, of corrupted data. It's a data storage problem. And what's happened is you've been hacked. Plain and simple, it's just like your hard drive on your computer has been hacked. You've got a virus, right? Well, virus is something different in biology, but you get the idea, right? It's a corruption of what you expected the information on your hard drive to be reliable and normal and functioning, and then all of a sudden, for some reason out of the blue, it's not, right? And so what the cancer has done is it's affected your cells in a way that it's essentially reprogrammed them to do things that are not normal, that they weren't intended to do. So if you're going to get out of this, you've got to hack it back, right? You've got to kind of use the same tricks on cancer that it was using on you. If we're going to basically undo that damage, if you get a computer virus, you have to delete it from your PC, or you have to have some other software come in that repairs the information and puts it back to normal again, right? So we can either contain or reverse the attack. And so cancer is acting like a hacker, right? And a hacker is someone who exploits a complex system, like our biology, the biology in a cell, and bends it to his or her own will, right? So here's cancer, right? Cancer is that black hat hacker, that evil hacker. It's hacking you, though, in a very crude kind of way. I mean, cancer is a very daunting and very complicated process, but in some ways, it's simple because it's very brute force. It uses relentless, random assaults in huge volumes on your cell biology to create exploits until it finds one that catches, one that works. And as Vikas was mentioning in his talk, it takes certain types of damage to your DNA in a certain configuration for cancer to arise. He was talking about basically the gas pedal and the brakes and immune compromise as things that are characteristics of the development of cancer, right? Where we have damage to the brakes so that the cell can no longer stop the process, or we get the accelerator pedal stuck down so that the car runs away, or we evade the cops, right, with flying under the radar and immune surveillance. So these are all things they're tricks that cancer learns to use, and it learns it over and over and over and over again from scratch in every cancer patient. It's not something that cancer looks up on the internet when it gets into your system and it knows how to do it. It has to evolve those mechanisms independently, individually, in every cancer patient every single time. It's a really important point that we'll come back to in a moment. Now, on the other side of the fence, those people who put their hands down first in our game in the beginning there, they are the white hat hackers. They're the nerds and scientists who are the good guys, right? So what they're working on are the hacks to counter the hacks that cancer is bringing in to our DNA. And they're using all kinds of cool tools and weapons in this. I mean, heck, we've even seen that they have a proton cannon that they can use to attack cancer. I mean, it doesn't get any cooler than that, right? So what they're doing is they're using very intelligent methods of science to find the weaknesses and the exploits that can be turned back around against the cancer, right? So we're in the middle of a hacker war. That's what's going on here as cancer patients. Like it or not, you're now involved in that war. So if you're going to have the best chance of making it through, you need to get up to speed a little bit on the landscape and the terminology of cancer. And we've been doing a lot of that this weekend, but obviously one weekend is not going to be enough to kind of delve into all the details that are going to be necessary to stay on top of this. Now, you don't need to get an advanced degree or anything. You don't need to go and get a PhD in molecular biology. But you just need to learn a bit about the mechanics of your disease and some of the terminologies so that you can follow along with the front lines of the development of the therapies that are coming out and the diagnostics and things that are coming out so that you can have a hand in directing your own treatment. Because one of the things that we see over and over again is that the most successful patients are the ones who are not passive, who are not letting the disease and the treatment happen to them. So, so let's kind of zoom this in down into our field, into ocular melanoma a bit. So Vikas was just talking a bit about eye cancer. We've talked about eye cancer, of course, for this whole weekend. We throw these terms around. I wanted to kind of clarify some of these terms a bit as to, when we talk about what type of eye cancer each of us has. We talk about ocular melanoma, we talk about uveal melanoma, we talk about choroidal melanoma, conjunctival, and we've been through a bit of that already. So I think this picture, which I stole from Cure, does a pretty good job of kind of pointing out how all this breaks down. We like to use ocular and uveal in particular interchangeably, but they're not really interchangeable terms. One is a sort of a superset of the other, and I think that's important to understand. So just to reiterate this really quickly, so ocular is sort of the biggest blanket term over all of it, and then when we drill into the most common type of ocular cancer that we're working with, we're talking about uveal melanomas, and the uvea it consists of these three things, right? So it's the iris, the ciliary body, which is on either side of the lens here. It goes around the lens, and it's part of this pigmented bit that sits behind the retina, which is the choroid. So the choroid, the ciliary body, and the iris together form the uvea. So if the cancer occurs in any of these areas, in this pigmented tissue, then it's uveal melanoma. So uveal melanoma is a superset, again, of these melanomas. And then kind of over on the side here, as we've mentioned a few times this weekend, is conjunctival melanoma, right, which is quite distinct. It's really more like skin cancer or skin melanoma than uveal melanoma, genetically speaking. And that kind of brings us to an interesting point here. One of the things that kind of works in our favor with cancer is that it's kind of a dumb and predictable hacker. As I was saying before, it's very brute force, right? It's using large volumes of very random assaults, which in different tissues in the body tend to always produce very similar or categorically similar results. Particularly, I mean, cancers actually vary quite a bit in this regard. For instance, a cutaneous melanoma has more genetic variation, but in uveal melanoma, for instance, the genetic variation is pretty narrow as far as cancer goes. So when we, another image that I've stolen from Cure, and our friends who published this, the breakdown of the types of changes that occur in the tissue is pretty regular. It falls into these bins. So this is a picture from a really landmark paper that some of our friends here in Europe were part of that really breaks down uveal melanoma into 4 different subtypes. And this is relatively new stuff, but it's really important. And these things down here on the side, these are kind of geeky tools that we can use to sense what's going on in the DNA. And then we can use these to characterize the tumor. And we can look at how this breaks down into these different categories. So as a patient, it's becoming increasingly important to figure out where you land in this sort of genetic landscape, because it's going to become increasingly more important in terms of driving how your treatment and your prognosis will work. So let's kind of drill into this for a moment. You can see right away in this disease, there's a big split into these two big columns. And you've heard this over and over again this weekend and probably beforehand. This whole idea about disomy 3 and monosomy 3, and monosomy 3 being much more characteristic of high-risk disease. So who here doesn't really get what the terms monosomy and disomy mean? Yeah. These are technical terms. These are terms from genetics, right? So as an example of the kinds of things that you can quickly familiarize yourself with and that will really help you when you talk to your oncologists and to all your caregiving team going forward, let's kind of dive into that particular case as an example. So these are chromosomes, okay? So you have trillions of cells in your body. We saw that picture that Vikas put up where he was showing that kind of slice of skin and it had all those cells, right? And that was just one little teeny little spot on your skin. You have trillions. I think the number is something like 37 trillion human cells that make up your body. Every single one of those cells has a complete copy of your instruction manual in DNA. And it's written on these little things. These are your chromosomes. And they're basically like little hard drives. They store data. That's their function. They are data storage devices. You can see they come in pairs. And each one of these little sausages here on this picture is actually a tightly coiled up, long, thin string. So we can stretch that out into one big, long string. And that string is the strand of DNA, which has the coding of your program to make you on it. So all of your instruction manual all together is spread out across all of these chromosomes in every single cell. So in each of these strands of DNA, there's further structure. They're broken up into stretches of coding that are the individual programs for parts of your cells. Your cells have lots of moving parts and non-moving parts. They also have signals that they send to other cells and things like that. And each of these little instruction books has the recipes for making those parts. And we call those genes, right? So what happens in cancer is that these instructions get messed up, right? They get lost or damaged or rewritten. And when we have a normal component of DNA here like this, then everything's fine. But if we lose, say, one copy of one of these chromosomes, then things get out of balance. We don't have the complete instructions anymore to do things. So when we have a complete pairing like this on a particular chromosome, that's called disomy. It means we have two copies of that chromosome. And that's the normal state of affairs for most of these chromosomes, except for these guys down here. And when we lose, or we lose the function of one of the members of this pair, then that drops back to what we call monosomy. And in chromosome 3, there's an important gene that is one of the things that kind of puts the brakes on cancer development. And so if that becomes compromised, then things can get into kind of a runaway condition. So this is why monosomy 3 is kind of a big problem in our disease, because we're losing one of the brakes that can hold the cancer at bay, right? Does that make sense? Yeah, so kind of going back to this then for a second. So knowing your status for disomy or monosomy 3 can therefore have a big impact on what the course of your disease can be. And you can see there are other alterations and changes to DNA that are in this table. We won't go into each one of these, but they also are affecting basically the level of risk and also outcomes and what kinds of treatments you might be eligible for, or that might actually work or not work in your disease. So that's just kind of one example of the kinds of things that if you learn those things, you can help guide and help talk to your oncologists about the structure and the journey of your treatment plan. So this all kind of comes down to, if you know what's going on with you, and you know more about what's going on with your enemy, in this case cancer, then you're not necessarily going to win 100 battles, but at least you'll know the outcome, right? You'll have a better chance of understanding where things are going to go, and there'll be less uncertainty for you. So this is sort of my call for you to kind of dive in and learn a bit about the cancer biology. I have a blog that I've been maintaining for several years called Hack My Cancer, and it has some episodes on there that kind of go through the basic cancer biology, and I try to keep it at a level where you can be a complete beginner, you don't need any advanced degree, and I focus it strictly on cancer and on the cell biology that matters when you're talking to cancer researchers and to your clinicians. So feel free to take a look here. There's some translation into Dutch as well. I've been working with our Dutch friends and Bianca over here to get it translated into Dutch, and we're working on some other languages as well. And I welcome any comments or questions about that. There's a comment section on the blog as well, so I can carry on a dialogue if you have questions about what's up there. All right. Any Thank you. Thank you.
Any questions?
Does the presence of monosomy 3 increase the probability of all cancers then?
No, it does increase the aggressiveness of a number of other cancers, though, but not all cancers. It's cancers that are affected. There's a particular gene on chromosome 3 called BAP1, and mesothelioma is another cancer, for instance, that is affected by the compromise of that gene. So it's not just involved in uveal melanoma, but it's not all cancers. Cancers, there is a sort of no one set of mechanisms that's common to all cancers. Cancer is a very broad topic, and there are lots and lots of different kinds of patterns of compromise that are different from one cancer to the next. But they do obviously share some overlapping mechanisms, and that's an example between, for instance, mesothelioma and uveal melanoma.
Just referring to that example there of chromosome 3, and that's a pair of chromosomes. Just to clarify, does each one of them carry the same genetic message, or do they carry separate genetic messages, even though they are a pair?
Okay, so the short answer is yes, and the long answer is no. So you get one of the pair from your mom, and the other of the pair from your dad. Okay, so, and the overwhelming vast majority of the coding on those molecules is exactly the same. It's what makes us humans and not bananas or chimpanzees, right? But there are key places where hereditarily, for instance, things are different. And they might lead to different traits, like different hair colors or different susceptibilities to disease and those sorts of things. But they are they're very small spots spread out throughout the genome, and for the most part, they're identical. But where they're not identical matters because it can change, what makes you you, right? What tends to happen, like the reason why something like monosomy 3 is a problem, even though you have 2 copies normally of the BAP1 gene, when you lose one of the pair of that chromosome, now you just have the opportunity to have 1 functioning copy of that gene. And if you have really bad luck and you inherited a non-functioning copy of that gene to begin with, and you happen to have lost the only functioning copy that you have, now you have no functioning copies, even though you have 1 copy of that whole chromosome still left, right? Or you can have a mutation that occurs on that functioning copy that knocks it out. And then you have no functioning BAP1 gene, and the brakes come off, and the cancer runs away. Does that make sense?